let's start off by recalling the definition of the tangent function. So recall. Nice and simple, tan of theta is the ratio sine of theta divided by cosine of theta. So as I've just said, this is pronounced tan theta, but really it's tangent of theta. Tangent of theta. So just to reiterate, this is the definition of tan theta, right? This is the proper definition of tan theta. We'll see that we can interpret this in various ways with right angle triangles. All of this sine, cosine, and tan. But before then, we need to understand them as functions, which is much more important. And again, this only really makes sense as long as cosine of theta does not equal 0, right? Otherwise, I'd be dividing through by 0, which doesn't make any sense. Right, so first of all, cosine and sine by definition are the x and y coordinates of positions on a unit circle given by an angle theta. So let me just remind us what that means. So I'm going to do a geometric interpretation, maybe is what I should say first. So I want to give a geometric interpretation of what tan is. One that's as natural as the proper geometric interpretation of sine and cosine. So let's start off by drawing a unit circle. Seems pretty good to me. So this is a unit circle, of course. This is your x, this is your y. 1, minus 1, 1, minus 1. And what's the deal? Well, if we take an angle theta, that gives rise to a position. So I'll do 1, which is quite simple. It gives rise to some position here, and this position is by definition cos of theta, comma, sine of theta. So by definition, cosine is the x-coordinate of this position, and sine is the y-coordinate. Okay, well let's think a little bit about this. What's the slope of this line? So this straight line I've drawn. So the slope is equal to what? Well, the slope, by definition, so there are several ways to think about this. I could think about it in terms of my usual slope formula for two distinct points. So in particular, down at the bottom, the origin here, this is 0, 0, remember. So what would the slope be equal to? It would be the difference in the sine, the difference in the x, y coordinate, sorry, so sine theta minus 0 divided by cos theta minus 0. Well, that's actually equal to tan theta. Really nice fact. And just to really make sure we understand, this is equal to, if I'm going to use the usual slope formula, sine theta minus 0 divided by cos theta minus 0. Okay, it's just my formula for the slope of a straight line with two distinct points. So it's like y2 minus y1 divided by x2 minus x1. And that works anywhere. It doesn't have to be just in the first quadrant, it can be any position at all. So this is a fantastic fact, right? This gives me a really elegant geometric interpretation for what tan is. And this is going to be really useful when it comes to graphing it. So let's think about the graph. So we're going to see the graph of tangent is really very, very different than the graph of sine and cosine. So let's take a moment to think about what I'm going to see in this story. So I'm going to interpret tan of theta as a slope of a straight line. So for example, in fact, let me kind of start drawing this. So let me kind of draw a graph. So we'll do theta and we'll do it to y. So I'm going to try to graph y is equal to tan of theta and just see what happens. So to begin with, so at 0 would be this position. That line there is horizontal, its slope 0. So I know at 0 I'm going to have to be 0. So right here. Let me mark a few other positions on this now, just so that we've got some positions which we are going to use as reference. So let's mark the position pi over 2, let's say. Let's mark the position pi. So that'll be here. Let's mark the position 3 pi over 2. So let me make that a little bit higher. And let's mark the position 2 pi, shall we? So 2 pi. So let's write it here. Okay, so what do I know? Well, this is kind of interesting, but x is equal to 0. Okay, you're right here. Oh, sorry, theta is equal to 0, your slope 0. So you start off at 0. All that happens, well, the slope now is going to be positive. I suppose it's going to go up to this point here where it becomes 1, right? And that would correspond to what? It would correspond to angle pi over 4, I think. So kind of 45 degrees if you're going to think about it in degrees, which you really shouldn't do, but still. And then what happens? Well, as I get closer and closer to pi over 2, things start to go a bit haywire. You see the slope is going to get bigger and bigger and bigger and bigger and bigger and positively. So it's going to get huge, huge, huge. And at pi over 2, it doesn't make any sense anymore. There's no concept of a slope of a vertical line because the formula breaks down. And I can't say the slope is infinite because that doesn't make any sense. Infinity is not a number. So what I think is going to happen is between 0 and pi over 2, I'm going to get bigger and bigger. I'm going to start off at 0 and I'm going to get larger and larger and larger without any bound at all. So what does that mean? Well, it actually means it looks like the following. So I'm going to draw a vertical line here. So what ends up happening is the following in the picture. You end up with a straight line that gets bigger and bigger and bigger like this, getting closer and closer into this line. But it's growing, growing, growing. And it never touches it, right? Never touches it. It just gets larger and larger and larger. What about on the other side? Actually, no, let's see what happens as I kind of wind around. This is a really nice exercise. Okay, so it doesn't make sense here, but what about if I'm a little bit on this side? So I'm a little bit bigger than pi over 2. Well, now the slope is massive, but it's negative. So now suddenly I'm negative, 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 but again less and less negative until eventually I'm back to 0. So this is crazy, right? What that means is when I graph this, I'm going to have a situation where I'm very big and negative when I'm a little bit bigger than pi over 2. But I'm going to go down to 0 when I hit pi. So again, a little bit bigger than pi over 2, negative and massive, go around until I hit pi, I'm back to 0. So then what happens? Well, the same kind of story. Now I'm 0, but I'm getting bigger again. Bigger, 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 bigger slope, bigger slope, bigger slope, and it's getting huge, huge, huge. So it's going to be the same basic story. So let's draw another kind of a guideline mark here. And it's going to do the same thing again. It's going to go up like this. And then what happens? Well, past this point, same story as in the second quadrant. A little bit bigger than 3 pi over 2. I'm negative, very, 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 very negative, right? So a very big negative slope. But then less and less negative, less and less and less and less until I hit 0. So that would mean it's going to look like this. Very big and negative. Very big and negative until it hits back to 0. And then the whole thing is going to repeat again. It's all going to repeat like this. So what does that mean the graph looks like? Well, I think basically it's going to be this essential pattern repeated, right? It's got to be 2 pi periodic at least because of the fact cos and sine are 2 pi periodic. There's something kind of special happens here though, so let me kind of just mark in the rest. So it's a bit hard to get the scale perfect, but we're going to do our best. It's not too bad there. Yes. So on the other side, it's kind of the same thing repeated, so it looks like this. So it's really different looking than sine and cos. It's these kind of infinite elongated kind of S-type things almost. So just to mark these numbers, this would be minus pi over 2. This would be minus pi. This would be minus 3 pi over 2. And then, of course, a little bit further on, it would be minus 2 pi. So that's what the graph has to look like, thinking carefully about what the slopes are. Okay, and first of all, I have what I've already seen before turning up here. I've got something very similar to what I saw in rational functions. So remember, in rational functions, when a point wasn't in the domain, there were two options. Either you were a removable discontinuity, it's called, which means there's just a hole in an otherwise perfectly fine graph, or there's some nightmare going on when the graph is getting bigger and bigger in the positive or negative direction as you get closer into this point that's not in the domain. That's called an infinite discontinuity. Well, we've got exactly the same thing happening here. So these vertical lines correspond to what we're going to call infinite discontinuities. These are going to be things you're going to study in much greater depth in calculus. It's important you kind of recognize them here at least. So what these really correspond to is the above line being vertical, which implies we have an undefined slope. When I say the above line, I'm talking about this line here. So at these positions, basically, you have a vertical line that has an undefined slope. That's exactly what you're seeing with these strange kind of vertical lines, if you want. Now, the graph is pretty distinctive. It's a graph I think you need to internalize. You've got to look at it for a while and memorize it. Something really interesting the graph does show is that this isn't just 2 pi periodic. So it's definitely 2 pi periodic, right? Because sine and cos are. But what I mean by that is if I take a block of length 2 pi, for example, like that, well, it clearly repeats, right? If I move that around, it repeats. But it's actually better. Something of a miracle happens. And it's not just 2 pi periodic. This guy is actually pi periodic. So this length here is pi. That repeats in blocks of pi. So tan of theta kind of picks up this extra periodicity. It's kind of a cool little fact. So tan of theta is actually pi periodic. So it's a little bit better than 2 pi periodic. All right, let's now take the time to go through all of my kind of standard properties that I'm used to listing out for my functions. So let's begin with the domain, shall we? Let's begin with the domain. So what's the domain equal to? The domain is equal to, well, this is pretty nasty. This causes a lot of confusion. So the domain is all points where I'm away from these, okay? And this really actually, if you think about it, is corresponding to the fact that cos of theta is equal to 0. These positions are all the same as cos of theta being equal to 0. That was something we've already looked at. So really what we want to do is come up with a nice way of describing these positions. So this would be all positions, so all x such that x is not equal to pi over 2 plus k pi. It's a bit of a mouthful, isn't it? So this is an integer. So for example, pi over 2 is just there, plus pi is over here, minus pi is over here, minus 2 pi is over here, plus 2 pi will be over here. So we want to avoid these points. So as I said, the only real problem is the cosine being 0. And that's exactly what we're picking up here. So we're basically just listing the same thing as the zeros of cos. So only problem is cos of theta is equal to 0. And as I said in the previous video, cos of theta equals 0 if and only if, well, x is equal to pi over 2 plus k pi. And we can see it in this picture above, right? Very nice, very nice. So what's the range? So I think that's quite difficult, right? I mean, it would be awful to try to write this down, for example, as a union of intervals, because you've got infinitely many, right? You would have, it's just terrible, you'd have this interval, then this interval, so it would be really grim to have to write down. It's kind of better just to write it like this. So next, let's do range. Range, thankfully, is much easier. Range visibly is everything. And we can see that, let me draw a smaller version of this. We don't need the entire graph to see it, we just need a piece of it. And we can see it with these elongated S things. So remember what the graph looks like? It looks kind of like this. Dot, 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 dot. So visibly, if I'm doing my usual green for range, it hits every single Y position. So you don't need the entire graph to do that. You just need a piece, for example, between minus pi over 2 and pi over 2. So very nice. The range is the whole thing. That also tells us, that the function is unbounded. Very different than sine and cos. Unbounded in both directions. So it's not bounded above or below. Neither above nor below. Very nice. Okay, what about increasing? Now this is one of these terrible subtleties that can super mess with you. It harks back to that local to global business we talked about a long time ago. So, is it increasing? Well, overall, no. It's only going to be increasing if I restrict to certain intervals. So tan of theta it's increasing on the interval, well, the open interval, because I'm not defined at the endpoints, this guy. It's increasing on this. So visually, I mean, that's exactly what this is, right? You can see it. Let's get rid of some of this other stuff. So it's most definitely increasing, as long as I am restricting. So maybe I should get a little bit bigger. So this is my pi over 2, and this is my minus pi over 2. So visibly, it's increasing. And it's increasing on all of these types of blocks, right? So it's not just there. If I kind of move this by pi, it's the same deal. It's increasing on this, and similar blocks. However, and this again is delicate, it's not increasing overall as a function. It's not globally increasing because it doesn't satisfy the appropriate property for all possible inputs. So this is really delicate, right? So let me just show you. So warning, tan of theta is not increasing overall. So just as a quick example, if I take pi over 4, I observe it is strictly less than pi. Now, if tan was increasing, tan of pi over 4 would have to be strictly less than tan of pi, wouldn't it, right? Now, tan of pi over 4, let me just talk about that a second. What's tan of pi over 4? Let's go up to this. I've already mentioned this, but it would correspond to the position which is at 45 degrees around. Pi over 4 in degrees is 45 degrees. So it's exactly there. So that actually makes cos theta and sin theta completely identical. The x and y coordinates are the same. That means their ratio is equal to 1. So that means tan of pi over 4, and we'll see this again in other examples, this is equal to 1. What's tan of pi? Well, tan of pi would be, again, it's the slope of the straight line across to here. Well, that's 0. Sine of pi is 0 if you want. So this is 0. But that's the wrong way round. It doesn't preserve the inequality. So this really is because of the following fact, right? It's because of these evil infinite discontinuities, really. So just visually here, what's happened is, so I can zoom in. What's happened is I've chosen the position pi over 4 here, and I've chosen the position pi here. So to be increasing, I would need to be larger or higher up at pi than at pi over 4. So this is pi over 4. This is pi. But the problem is that's 1 and this is 0. So it's lower down. So overall you're not increasing. So this is incredibly subtle. You've got to really understand the meaning of increasing overall. Overall it doesn't work. So if I say a function is increasing, full stop, it means it's increasing in the entire domain, and that it's not true here. It's true if I restrict. If I restrict to be strictly between these two, it's all good, but not if I allow the whole domain. So this is kind of an important, delicate point that is important to understand. Okay. So increasing on these nice intervals. What else? Well, it's odd. There's another nice fact. And you can see this in various ways, but let's take the time to do it carefully, shall we? So it's an odd function. Tan of theta is odd. It's an odd function. Let's check the actual definition. So tan of minus theta is equal to sine of minus theta divided by cos of minus theta, all right? But now sine is odd and cosine is even. So this has to be equal to minus sine of theta divided by cos of theta. And that has to be equal to, well, it's just minus tan of theta, which is exactly the necessary condition for being odd. So this key point here, sine is odd and cosine is even, something we saw last time. Lovely. This kind of corresponds to the fact, if you take the product or the quotient of an odd and an even function, that has to be odd at the end of the day. Kind of a property or something very close to a property that we saw before. Again, tan of theta is massively not one-to-one, just like sine and cosine. So it's going to make doing inverses very delicate. So tan of theta is not one-to-one. How could it be? It can't be. It's pi periodic. It repeats. So upstairs, if I took this graph, in fact, let me just grab it. So I just want to immediately show you why it's so bad. Need to scale it a little bit. Give me 1 second. So let's shrink this down. Well, visibly, disaster strikes anywhere, because if I take any horizontal line, it crosses at infinitely many positions. No good at all. Horizontal line test fails miserably. So last, let's think about the zeros. We can basically see them in this picture when it comes down to it. So they correspond to when sine is 0. So the x-intercepts, or the 0 values, tan of theta is equal to 0. So if and only if, I might as well do the justification here. Sine of theta is equal to 0, of course, because it's the numerator. When sine of theta is 0, cos is never 0. They don't match up. They're kind of out of sync, or out of phase, if you want to say it like that. This is only if and only if, remember, theta is equal to k pi, where k is an integer. And let's just do this with the unit circle. We could, of course, do it above. You can see all these positions above. You can see them here, 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 all of this business. But let's do the unit circle to illustrate the idea, because it's quite nice. So remember how it works. If I draw the unit circle, if I attempt to draw the unit circle. So what's the deal? If I'm taking an angle theta, it gives me one of these lines. The slope of this is the tangent of that angle. And there are only 2 points where you're going to get slope 0. So these are the only points. It's really nice. Only points with slope 0. So that corresponds to 0, and I suppose an integer number of revolutions, half revolutions around the circle, which we can represent as k pi, where k is any integer. If k is positive, they're counterclockwise, and if k is negative, they are clockwise. So this is tangent, and it's vital you understand tangent. It's one of our kind of 3 most important trig functions. Sine, cos, and tan by a mile are the ones that we look at the most. You really need to internalize the graph, I think, more than anything else. You should interpret it. It's really nice to think about it in terms of these slopes of this line. It's really nice. That tells you a lot, and it gives you a lot of immediate intuition for what tangent has to be. If you're trying to do it in terms of sine and cos, it's just very confusing, because you're like, well, okay, sine would be this, cos would be this, what's the ratio? My intuition is not very good for that, but the idea for the slope is really natural. So I think this is a lovely way to interpret tan, and it makes the graph pretty obvious, relatively speaking.